welcome to the 49th lecture in this series. So I'll continue talking about tensors and forms. In this lecture, I'll discuss a bit about alternating tensors, which are also called sometimes we say alternating forms or alternating tensors. So last time I talked about symmetric tensors, which is the sort of the opposite of an alternating tensor. So let's say alternating so we look at a alpha in what we call lek(v). K multilinear maps on V. Alpha is alternating if whenever we interchange two of the input vectors, we get a minus sign. For any so recall that we called a tensor symmetric if whenever we flipped two of the input vectors, the sign did not change. The value did not change. Here the value acquires a negative sign. So just like in the symmetric case, we have a nice characterization of alternating tensors in terms of the symmetric group action on lek(v). So proposition the following are equivalent. Alpha is alternating. The second thing is that sigma alpha, which I defined in my last lecture, sigma times alpha or sigma acting on alpha is equal to minus 1 to the power sine sigma alpha for any sigma in the symmetric group on k letters. The third thing is sigma if whenever two input variables are equal. So here I want vi equal to vj for some I not equal to j, greater than or equal to 1, less than or equal to k. The fourth thing is a similar thing. This is 0 if the set of vectors v1 up to vk is linearly dependent. Right. So I won't go into all the details. I'll briefly discuss some parts, and let's start with the equivalence of 1 and 2. So the proof is very similar to what we had for symmetric tensors, namely let's assume 1. Well, before I do that, maybe I should point out the easier one. 2 implies 1 is follows by taking given I and j, let sigma be the sigma, take the permutation be the permutation which interchanges I and j and keeps the rest fixed. So this is what we call the transposition. Take sigma to be the transposition which interchanges I and j and keeps the remaining rest fixed. Right. Then sine sigma, the way we defined the sign of a permutation was, you just had to write it as a product of transpositions and then just count how many there are. If they're even number, we say that the permutation has the sign is 1. If they're odd number, then the sign is -1. So here this exactly sigma itself is a transposition. So the sign would be -1. It's exactly 1. Well, given this, then you just go back. So we are assuming 2. Therefore, sigma dot alpha would be minus alpha, i.e. So if I act it on any vector sigma dot alpha acting on v1 up to vk would be minus alpha acting on v1 up to vk, and this by definition is alpha v sigma 1 v sigma k and since all sigma does is interchange I and j and keep the remaining numbers fixed, remaining indices fixed. So what we get is 1, well, assuming that I and j are not 1 or k, so it will interchange. So wherever vi occurred, vj will occur, and wherever vj occurred, vi will occur. Oops, so sigma k would be just k. Again, assuming that I and j are not 1 and k, otherwise we would have to do the swap in the first and last one of the 2 slots. So the equality of this and this is precisely the alternating condition that we had started with. Well, and 1 implies 2 follows from, again, just like in the symmetric case, we write sigma, start with the sigma. First, let's start with let sigma belong to sk. We can write sigma equals tau 1, tau n, where tau I in sk are transpositions. And once we have this, sigma dot alpha is tau 1 tau n dot alpha. So we know that first I can do tau n and then do the rest. And we know that we are assuming that the form is alternating now, and the form being alternating amounts to, as the first step shows, it amounts to saying that the action of any transposition will reverse the value, the sign, keep the magnitude of the value the same, but the sign gets reversed. So this will be, I'll pick up a minus sign from each one of these. So after the first step, I'll get minus alpha, and now there are tau n minus 1 transpositions here. So and then now I do again this tau n minus 1 of, so each time I'll pick out minus 1 alpha, minus 1. So it will be a product of n of these minus 1s, and this is precisely what we called the sine of sigma times alpha. Now 3 and 4 again directly follow from 1. For instance, let's say 3, actually, so if I have 1, 1 implies 3. That follows just by putting Vi equal to Vj. Put Vi equal to Vj. Then if I interchange these two, then sigma V1, Vi, Vj, Vk equal to minus this is from the alternating condition, but since Vi and Vj are the same, I can also write this as V1, Vj, Vi, Vk. And sorry, here I should make it, I haven't interchanged the two. So this should be Vj, Vi. Notice that the leftmost term and the rightmost term are the same except for a negative sign. So therefore each one is equal to 0. And as for 3 implies 1, if we know that whenever two variables are the same, the value is 0, and if we know that and we would like to see that whenever I interchange I get the required thing, the standard thing to do is consider sigma of V1 Vi plus Vj in the ith slot, Vi plus Vj, oops, not I plus j, Vi plus Vj in the jth slot, and then Vk. Now I know that this is 0 because these two input vectors, I have Vi plus Vj in 2 slots. So I have this, so I expand it out using the multilinear property. So I'll get 4 terms, V1, Vi, Vi, Vk plus sigma V1, Vi, Vj, Vk plus sigma V1, Vj, Vi, Vk plus sigma V1, Vj, Vj, Vk equal to 0. And again by hypothesis this is 0 and this is 0 as well. So I am left with 2 terms. One involves Vi first and then Vj second, the other one is Vj and Vi. So these two have to be negatives of each other. So that proves that 1 and 3 are equivalent. And once you know 3, and it's easy to see that 3 and 4 are equivalent as well. For instance, if 3 implies 4, one can do the following. If I know that any two input variables are 0, and I start with a linearly independent set. Let be linearly dependent, sorry, not independent, linearly dependent. Then by definition I have this equal to 0. Ci, all the coefficients are just real numbers. Ci in R, and not all of these 0. That's the part of being linearly dependent. So let's say, suppose, just for convenience, let me take C1 not equal to 0. Then I can write V1 equals, as a linear combination of the others, minus C2 by C1, V2 minus CK by C1 VK. And then once I have this, I evaluate sigma V1 VK. Instead of V1, I plug in this whatever I just had, this linear combination here. So minus C2 by C1 V2 minus CK by C1 VK, and here I would still have V2 and VK. Then I expand it out using the multilinear property. So I'll get minus C2 by C1 sigma V2. Well, the remaining stuff I keep as they are. So this would be V2 VK minus C3 by C1 sigma V3 V2 dot VK, etc. So I'll have K terms. And notice that each one of these terms, in each one of these terms, two of the input variables are repeated. First one it's V2, V2, second one V3, and here another V3 would be there, that would repeat. So all of these are 0, so therefore I get this equal to 0. And 4 implies 3 is also straightforward. 4 implies 3 is the condition that if you know that they are all linearly dependent, then inputting, if I so let's say let I start with a set of vectors with Vi equal to Vj for some I not equal to j. Now the point is that this is automatically linearly dependent. This linearly dependent because I can put 0 times V1 plus 0 times V2 dot plus 1 times Vi, and go on putting zeros in everything except when it comes to the jth slot, minus 1 times Vj equal to 0. So this is linearly dependent. So therefore I can conclude that sigma V1 Vk equal to 0. Right. These are various ways of thinking about alternating forms. Now I had briefly talked about pullbacks under linear maps of a K tensor. So let's go to that and have a let's have a look at that in the context of symmetric and alternating tensors. So let's first look at the case of symmetric tensors. So these are examples involving symmetric and alternating tensors and pullbacks. So let's look at a linear map T from Rn to, let's look at this case. Vector spaces are Rn, just one vector space Rn, and I want to look at the form alpha in L2 of Rn, the dot product alpha of Vw is the inner product or dot product of V and W. Now let's consider T star alpha. So alpha can be regarded, of course, since the target and domain are the same, alpha is present in both domain and target, but I'm looking at alpha on the target. So since the pullback operation proceeds in, you have to start with a tensor on the target vector space. So T star alpha acting on VW would be, this is by definition alpha of TV TW, which we know is TV TW. So essentially the pullback operation of acting on VW is the inner product of, first you do T and then you take the inner product. Now if we want to know when is T star alpha equal to alpha, T star alpha equal to alpha if and only if inner product of TV TW equal to inner product of VW for all VW in Rn. Well, we know exactly when this happens, i.e. the matrix of T is an element of On, i.e. the matrix of T is an orthogonal matrix. So to say that T belongs to On or the matrix of T belongs to On is the same thing as saying that the pullback of the inner product under T is the same as alpha. Now this is one example. The second example is again T from Rn to Rn. This time let's look at an alternating tensor, and the only one we have looked at so far. Well, we have looked at a couple. One of them was the determinant. So alpha, right, before I proceed, perhaps I should point out that let me write it here. The set of alternating tensors, K tensors, forms a subspace of LKV denoted by V. Well, this is not exactly standard notation, so let me denote it by, we denote it by AKV. So this is a subspace of LKV. So it's easy to check that if you add two alternating K tensors or you multiply it by scalar, again what you get is an alternating K tensor. So it's a subspace of LKV. So now let me start back to this problem, back to this example. So alpha in AKV is given by alpha of V1 up to Vn is determinant of V1 up to Vn, where as usual these Vi's are regarded as column vectors. Now we want to again look at the same thing, which is, let's look at T star alpha. The claim is that T star alpha is actually just the determinant of T times alpha. And this example is going to play a crucial role later on when we talk about integration on manifolds. So in fact, this is one of the main reasons, this specific formula is one of the main reasons why one even talks about alternating forms and so on. Now the fact that determinant pops out like this, in this example of course we are starting with a determinant, so it's not that surprising that determinant is coming out. But we'll see that alternating forms are very of any degree. So here, right, okay. So here I should be a bit careful. This K is actually N. I'm looking at, since I'm inputting N vectors, so this K is AN, the same N as the dimension. So the point is that I'll get a square matrix here. V1 up to Vn will give me a square matrix. Right. So as I was saying, yeah, okay. So now we want to, so in order to prove, first note that to see this, well, this is an N form and the right hand side is an N form as well. So we have to check, i.e. T star alpha acting on V1 up to Vn equal to determinant of T alpha acting on V1 up to Vn for all V1, Vn and Rn. At this point, I would like to say that it's enough to check this. We can assume V1 equal to E1, Vn equal to En without loss of generality. In other words, if I want to check that this equation holds here for all V1 V up to Vn, I don't lose anything by just checking it for a single choice of V1 up to Vn, namely V1 is E1, Vn is En. And why is this? It just follows from the fact that if I start with any arbitrary V1 up to Vn, I can write V1 as summation A1j Vj, Ej. In other words, I expand it out in terms of the basis vectors, standard basis vectors, dot 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 Vk equal to sigma Akj Ej. Well, right, and then once we have this, then if we evaluate, right, and if we evaluate T star alpha on this, we'll see. Well, rather than finish the calculation now, let me stop here and resume with this in my next lecture. Okay, thanks.